Welcome back to Engineering 5213, Tools of Operations Research. This is Lecture 5, Part 2. We're going to continue our discussion of network optimization. So in the last part, we examined two kinds of network optimization problems, one called the transportation, in which case we're trying to decide how much of something to ship or transport between some number of source locations where the product or the goods or the thing to be shipped is currently to multiple destination locations, and each source destination pair incurs some kind of unit cost, the amount it costs to ship along that route. And what we want to find is a way to ship all the goods that are needed at each destination from the available goods at each source in order to minimize the total cost. We also looked at an assignment problem where we are assigning some number of things to some other number of processes. And in the case of our example, we had swimmers and swimming strokes in a relay team. And that's really a special form of the transportation type of problem in which each of the capacities, that is how many things each source, or in our case swimmer, can be assigned to, is limited to one, as well as each destination, the strokes being assigned, is limited to being assigned to only one swimmer. So it's a special kind of transportation model in which the capacities and demands are all equal to one. As we look back to the first example we had of the three plants that had goods shipping to the four warehouses, we found the optimal solution, which involved mostly some cheap shipping routes, but a few more expensive routes that might have been a little unintuitive, but in order to meet the demands, given the capacities of each source or plant, that's what had to be done. So if we look back on the screen here to the solution, we can represent this solution using the diagram model we talked about last time. So if I refer back to the whiteboard, we had three possible sources, three locations that can be shipped from, there we go, Minneapolis, Pittsburgh, and Tucson, and four destinations, Atlanta, Boston, Chicago, and Denver. And what we did is we found that each source had a capacity, the amount that could be shipped to it, and each destination had a demand, the amount that it wanted shipped to it. And those were something like 7,500, 8,500, 9,500, and I believe 8,000. And what we found was the optimal solution. So if we look back on the Excel sheet, we found that the optimal solution involved shipping from Minneapolis. All of its 9,000 capacity was shipped to Chicago. Okay, so I'm going to represent that by a line from Minneapolis to Chicago labeled with 9,000. And all of the goods in Pittsburgh, which had 12,000 capacity, was split and shipped to two different locations. Some of it was shipped to Atlanta, 3,500 was shipped to Atlanta, and the remaining 8,500 was shipped to Boston. Okay? And so forth. So we can find where did Tucson send its goods, and it sent its goods to three different locations. Some of it went to Atlanta, 4,000 of it went to Atlanta. Some of it went to Chicago to meet the demand in Chicago that wasn't quite met by Minneapolis, which was 500 units. And then finally, the remaining Tucson capacity was sent to Denver, and that was the 8,000 that Denver required. So again, looking at our network diagram, we have 9,000 units being supplied by the capacity of how much Minneapolis can be supplied. And in this case, the only edge coming from Minneapolis is one going to Chicago, labeled with the 9,000 that Minneapolis had available. So all 9,000 units or products from Minneapolis went to Chicago. Now Chicago needed 9,500. So obviously, if 9,000 came from Minneapolis, we need another 500 from somewhere. And we can see readily from the diagram that that 500 came from Tucson. Tucson sent 500 to Chicago. It also sent 8,000 to Denver, okay? And that's out of the 13,000 capacity that Tucson had. Now, if Tucson had 8,000 sent to Denver, 500 sent to Chicago, that's 8,500. Technically, Tucson had 4,500 more capacity to send. Only 4,000 of it was sent from Tucson to Atlanta, okay? So Atlanta did not send all of its 13,000. So 13,000 was the capacity of Tucson, but only 12,500 was sent out because not all the capacity amount of product was needed at every destination. Now, of course, Tucson sent 4,000 to Atlanta because Atlanta got the rest of what it needed. It needed 7,500. It got 4,000 from Tucson. The rest of what it needed, 3,500, came from Pittsburgh, where presumably it was cheaper. But Pittsburgh couldn't send any more than 3,500 to Atlanta because it was already sending all that Boston needed, 8,500, coming from Pittsburgh. So this is just a visual representation of the solution we found, okay, in the linear optimization, the network optimization problem that we did. Okay? So just a visual representation of how we have source locations, we have destination locations. Sources have capacities, destinations have requirements, okay? And somehow we have to match up every requirement or every demand needs to come from one or more of the sources, but each source cannot send out more than it is limited to, more than its capacity. Now, one other thing we could consider looking at is using optimization sensitivity to describe or define how solutions would change, how the optimal solution, in this case the optimal shipping routes, would change with a change in some parameter. For example, let's look at the amount that needs to be shipped from, let's say, Boston or Minneapolis to Boston. Okay, so right now we have that listed as 56 cents. Now, Minneapolis shipping to Boston, actually in our optimal solution, we did not ship anything from Minneapolis to Boston. Okay, so we might ask the question of how cheap would this rate, this 56 cents, how cheap would that have to be before it's more advantageous to ship from Minneapolis to Boston than from Minneapolis to Chicago, which is what we did, and from Pittsburgh to Boston, which is what we did. Okay, so let's say we input out here using the Analytic Solver Platform Parameters button. We're going to do a optimization parameter, and we're going to say, well, let's use a lower bound of, let's just use 0. Okay, if it costs 0 cents, and an upper bound of 56 cents, so that's what we have now. So that's our definition of the range of values we want to try. And we want to try those here in D3. So we need to set D3 equal to the cell I3 where I put that parameter. Okay. So D3 is equal to I3. I3 uses the optimization parameter function to define a range from $0, 0 cents, to 56 cents. Okay. And now we can run a report, an analysis report, using the optimization parameter analysis buttons to say how would the optimal solution change given changes in the parameter as defined. Now before I do that, I'm going to make things a little bit easier by defining a few cell names. So for example, the total cost cell in B15, I'm going to rename total cost. And since we know Boston is currently getting its supply from Minneapolis or from Pittsburgh, I'm going to name that cell D10 the Pitts to Boston cell. And similar for the Minneapolis to Chicago cell, and similar to the Minneapolis to Boston cell. So I've given those cell names, and now I will run the optimization parameter analysis, that is optimization sensitivity. Obviously, the parameter that's going to get changed is the one I put in I3, and I'm going to use 57 different points because we have a range from 0 to 56. And the variables that I want to measure the difference of in each case, in each different value for the parameter, is those three variables that we can change, the Minneapolis to Boston, Minneapolis to Chicago, and Pittsburgh to Boston, as well as the objective function, total cost. So let's generate that report. And this report is going to allow us to answer the question of how cheaply does the shipping from Minneapolis to Boston have to be before we no longer ship from Minneapolis to Chicago and from Pittsburgh to Boston. So here we can scroll down and find at the bottom the base case that we had before at 56 cents shipping Minneapolis to Boston. We don't ship anything from Minneapolis to Boston. We ship everything from Minneapolis to Chicago and everything from Pittsburgh to Boston for a total cost of $12,025. And if we look up through this report and find the first time at which the solution changes, so apparently once a route from Minneapolis to Boston becomes as cheap as 25 cents, we suddenly decide now we should ship from Minneapolis to Boston 4,000 units. Not the total of what Boston might need, because we're still shipping some of Minneapolis's goods to Chicago. We're still shipping some of Pittsburgh's goods to Boston. But for the optimal lowest cost, at 25 cents, it becomes feasible to ship some of Minneapolis's goods to Boston. If we further look up the table, that pattern continues only for 2 points before we find if the route from Minneapolis to Boston is as low as 23 cents, we should ship all that Boston needs from Minneapolis. All 8,500 that Boston requires should come from Minneapolis. 500 units still available in Minneapolis, because Minneapolis had a capacity of 9,000. 500 units can be shipped to Chicago, and obviously nothing is being shipped from Pittsburgh to Boston, because Boston is now getting everything it requires from Minneapolis. But it requires that route to be so low, the shipping to be so low as 23 cents versus what it was, 56 cents. Okay? So that's using an optimization sensitivity to answer questions like that. Let's do one more quick example. And let's say, what if the Pittsburgh to Boston route was more expensive? Okay, so right now it's 30 cents to go from Pittsburgh to Boston, which is why we use that route in our optimal solution to ship everything Boston needs from Pittsburgh. But let's say we wanted to ask the question, what if this was more expensive? So here I'm going to change my cell I3 to be a lower bound of 30 cents, and let's do an upper bound of 60 cents. Okay, so a 30-cent range. And now I'm going to set the D4 cell equal to I3. Okay, so D3, the Minneapolis to Boston, is now back to 56 cents, but the Minneapolis to Boston cell is now equal to this parameter, which is going to range from 30 cents to 60 cents. And now we need to rerun a report. Well, let's name the Pittsburgh to Boston cell. We might also be curious in knowing how, once Pittsburgh might ship more to Boston, would it ship what's left to Atlanta? So let's name the Pittsburgh to Atlanta cell. And of course, if this becomes more expensive and Boston no longer gets product from Pittsburgh, maybe it'd get it from Minneapolis, or maybe it would get it from Tucson. So let's name this cell Tucson to Boston. And now let's run our report. So we're no longer interested in what Minneapolis ships to Chicago, but we are going to be interested in what Pittsburgh sends to Atlanta. And what Tucson sends to Boston. So we have the total cost and we have where Boston is getting all of its product from, Minneapolis, Pittsburgh, and Tucson, as well as where Pittsburgh is now sending its product to Atlanta, how much of it's being sent to Atlanta. And because we have a 30-cent range, I'm going to use 31 access points to generate my report. So again, at the base case of 30 cents, Pittsburgh sends all of the goods needed at Boston to Boston, and sends the rest of what it has, the capacity it has, to Atlanta. Once that cost becomes as high as 40 cents, so between 39 and 40 cents, suddenly at 40 cents, it becomes more advantageous to send less product from Pittsburgh to Boston, 4,000 less than before. That extra 4,000 gets shipped to Boston from Tucson, okay, versus that extra 4,000 from Pittsburgh is now being shipped to Atlanta. That is, it's become too expensive to ship so much from Pittsburgh to Boston that we'd rather ship more of Pittsburgh's goods to Atlanta and receive, okay, Boston's needed goods from Tucson. Now, we might ask the question, if we went to 40 cents from 30 cents of shipping Pittsburgh to Boston, and we decided no longer to ship 4,000 units from Pittsburgh to Boston, so 4,000 units times 10 cents a piece would be $400 saved. And yet, our total cost here obviously has a difference of something like $810. So we've saved $400, okay, by shipping, although it costs 10 cents more, shipping 4,000 less. But obviously we have the cost now of shipping Tucson to Boston and more of a cost of shipping Pittsburgh to Atlanta. So the amount of change in our total cost isn't going to be as simple as a 10-cent difference, because we've shipped fewer things for a 10-cent maximum. What we've now done is incurred more cost of a different route, and actually two different routes, Pittsburgh to Atlanta, Tucson to Boston. Okay. Now, just out of curiosity, if that price continued to rise, even up to 60 cents, we still send 4,000 units from Pittsburgh to Boston. We still send 4,000 units from Pittsburgh to Boston, even as high as 60 cents. We could have examined values beyond that and seen at what point does it become no longer advantageous to send anything from Pittsburgh to Boston, but we did not. Okay, so that's using optimization sensitivity to change the parameters of this model and ask questions like, how expensive would one particular shipping route need to be before the optimal solution would change in some way, and how would that, what would that change be? Okay, and what would the effect on the objective, the total cost, be as well? Okay. So we've talked about transportation. We've talked about assignment. Now let's look at a slightly more complex problem of transportation known as transshipment problems. And a transshipment problem is really just a transportation problem which occurs in two or more stages. That is, we have a set of sources, a set of intermediate destinations, and a set of final destinations, or possibly more stages of intermediate destinations in between. For example, let's look at a problem where a company must find the minimum cost shipping schedule. So again, we're minimizing cost, choosing which shipping routes to take advantage of, and shipping product from 3 factories. So the product is made in in 3 factories. It's shipped from there to 2 distribution centers where the product is maybe packaged, prepared for sale, maybe other things are added to it, it's put together. So made in a factory, sent to a distribution center for processing of some kind, and then shipped from a distribution center to warehouses. So now we have a 2-stage shipping process. Every product comes from some factory, goes to some distribution center, and then from that distribution center to some warehouse. So for example, let's look at some of the parameters that might be involved. So here we have a simple table of our 3 factories and 2 distribution centers, DCs we'll call them. D1 and D2, and the shipping cost per unit of each of those. And again, our factories have a capacity. That is a maximum amount of product that they can produce and supply to these distribution centers. But once at the distribution center, there's another stage where from each distribution center, D1 and D2, product must be shipped to one or more of 5 warehouses. So the end destinations are the warehouses, but they don't come directly from factory to warehouse. They first go through a distribution center. And warehouses have a requirement or a demand of how much product they need. And then obviously there are unit costs associated with distribution centers shipping to warehouses. So we have this problem. Let's go ahead and input this problem into Excel like we have before. Okay, so we have our factories, F1, F2, F3, and we have our distribution centers, D1 and D2, and then we have our factory capacities. Okay, so that's the first stage of the problem. So $1.28, $1.33, and $1.68 with the cost to ship to distribution center 1, $1.36, $1.38, and $1.55. Cost to ship to distribution center 2, and then the capacity of every warehouse is 2,500. Okay, so we'll format these as currencies. We'll put a border around them to make it obvious. That's what those are. But now we have a second stage problem. Okay, so now we need to also solve shipping from distribution centers, so D1, D2, ship to each of 5 warehouses. Warehouse 1, Warehouse 2, Warehouse 3, Warehouse 4, and Warehouse 5. Okay. Make it a little easier. Fit those all on the screen. Okay. And those have their own unit costs, which are 60 cents, 42 cents, 32 cents, 44 cents, and 68, and then 57 cents, 30 cents, 40 cents, 38, and 72. And our warehouses have a demand or requirement of 1,200, 1,300, 1,400, 1,500, and then finally 1,600. Okay. So again, these are unit costs, so we'll format them as currencies and distinguish them with a box around them. Okay. Okay. So now we can actually come away and start assigning cells for use as our decision variables. Okay. These are not dollars, these are numbers of product. So we'll just format them as general numbers. And we will also fill them with an orange color. We'll need to sum the values from each factory, because we need to constrain those things to be less than their capacities, less than or equal to their capacities. However, we're also going to sum the columns, although we don't have a demand on each distribution center. D1 and D2 don't have demands associated with them. We still need to know how much product came into the distribution center, because we're going to constrain that to be equal to how much product will go out. So we can't ship less product to distribution center 1 than we want to ship from distribution center 1 collectively to the 3 warehouses. So here, the sum of these rows in the second stage are going to have to be constrained to be equal the sum of the columns from the first stage. And then, like before, the sum of the columns here will be constrained to be greater than or equal to, really just equal to their demands of each warehouse. Okay, so these as well are our decision variables. Okay. And then finally, we have an objective, which is total cost. For which we can use some product like before to calculate the cost of shipping from each factory to each distribution center, and we're going to add to that another sum product of how much we ship from each distribution center to each warehouse. Okay, multiply it. And that will be our objective. So we have 6 decision variables in stage 1. We have 10 decision variables in stage 2. We're going to constrain the amount shipped from each factory to be no greater than its capacity. So you can't ship more than available. We're going to constrain the receipt of product at each warehouse to be at least as much, really as much, as its requirement. And then finally, we're going to have to constrain that what gets shipped into the distribution centers must be equal to what gets shipped out of the distribution centers. Okay. And then finally, we'll want to ensure on the engine tab that we still are using, assuming non-negative decisions. That is, we must have zero or positive values for each of our decision variables. So now we can run the model. So this is our model. Transshipment, meaning we're shipping from one set of sources to intermediate destinations, and then from those intermediate destinations to the final destinations, in such a way that we meet capacity, or don't exceed capacities, but meet demands, and of course that whatever we ship into a distribution center has to get shipped out. So the optimal solution found is that Factory 1 should send all of its product to Distribution Center 2, all 2,500. Factory 2 should send 2,000 of its product to Distribution Center 1. Factory 3 should sort of split, sending some to Distribution Center 1, some to Distribution Center 2, and then the objective, the total cost at this point, is a little over 13,000. Now, what gets shipped from each distribution center looks like it goes all to a single warehouse. That is, no warehouse receives product from more than one distribution center. What's interesting is to meet the demands of all the warehouses, we obviously didn't have to use all the capacities of the factories. That is, Factory 2 did not need to produce all 2,500 that it had available of the product. It only needed to produce 2,000 to minimally meet all the warehouse demands in as cheap a shipment route as possible. Okay, and then of course we can look up here and say Factory 2 shipped to the cheaper of its two distribution centers, Distribution Center 1. Factory 3, of course, had to ship to both, but Factory 1, it turns out, shipped to Distribution Center 2, okay, which was more expensive than it could ship to Distribution Center 1, but obviously Distribution Center 1 only needed a certain amount of product given which warehouses it was going to ship to. So even though it was cheaper to send from Factory 1 to Distribution Center 1, $1.28 versus $1.36, we didn't want to do that because having more product at Distribution Center 1 presumably would make it more expensive to get to the warehouses later. As you'll see, Distribution Center 1, it's only cheaper to send from Distribution Center 1 to Warehouse 3 and Warehouse 5. Okay, it's cheaper to send from Distribution Center 2 to Warehouse 1, 2, and 4. Okay, but again, Warehouse 4, it was cheaper to get its product from Distribution Center 1, okay, as opposed to Distribution Center 2. Minimal cost. Okay. Let's go ahead and examine what the solution for this would look like using a diagram like we had on the board for our transportation problem. So in the case of a transshipment problem, obviously we have more nodes available, or more nodes being used because there's two stages to the process. So we had factory 1, factory 2, and factory 3. Okay? Each had a capacity of 2,500. And we had two destinations for the product from the factories. That is, two distribution centers. And we had 5 warehouses. Which had differing demands, represented by 1,200 for warehouse 1 up to 1,600 in warehouse 5 in increments of 100. And our optimal solution found that factory 1 should send to distribution center 2, factory 2 should send to distribution center 1, and factory 3 should send to both. So we'll only draw lines here for routes, shipping routes that actually had a non-zero amount shipped on them. Okay, so factory 1 sent 2,500 to distribution center 2. Factory 2 sent 2,000 to distribution center 1, and factory 3 sent a combination of 900 to distribution center 1, 1,000 to distribution center 2. 1,600 to distribution center 2. And then likewise, distribution center 1 shipped its product to warehouse 3, 1,400, and 4, 1,500. Distribution center 2 sent the required amounts for each warehouse to warehouses 1, 2, and 5. So looking at the diagram, it looks something like this. 3 source locations, 2 intermediate destinations, capacities for the sources, and amounts shipped out of those sources to the intermediates. And then, of course, from the intermediates, there was shipping to each of the final destinations, the warehouses, which had demands. What we should see, of course, is that the demand for each warehouse is met, that is, the amount coming into it is met perfectly. So if 1,300 was required at warehouse 2, then 1,300 came in. Likewise, factories, if capacity was a certain amount, no more than that could go out. Now, in some cases, all of it did. In some cases, not all of it did. And likewise, whatever came into a distribution center, so in this case, 2,900 came into distribution center 1, that must be equal to what went out. So in this case, 2,900 as a combination to warehouse 3 and warehouse 4. And similarly for distribution center 2, which received 4,100 in and sent 4,100 out. Okay. Just a quick check to make sure that those constraints were met. So that is a visual representation of a transshipment model. So a set of sources, a set of intermediate destinations, and a set of final destinations. And then a label for each link representing the capacities of the sources, the amount shipped from each source to each intermediate destination, and the amount shipped from each intermediate destination to a final destination, and the requirement needed at each final destination. Okay, so that covers 3 of the kinds of network optimization models that we have available to us. A transportation model, an assignment model, which is a transportation model with all capacities and demands equal to 1, and a transshipment model, which is effectively a 2-stage transportation model. Okay? The only special requirement of a transshipment model is that you need to enforce through a constraint that what comes into an intermediate node also leaves that intermediate node exactly. So the income is equal to the output. That covers a few kinds of network optimization models. There's really one special kind more in which, unlike the transshipment model, where I just said that what comes in goes out exactly, there are kinds of network optimizations or processes which have yield. That is, not all that comes in may go out. There may be some inherent waste or loss, or what comes in may go out plus some extra. So there might be some extra interest added that comes out beyond what went in. So those are special kinds of network optimization problems that we call network optimizations with yields. And they're used for processes like manufacturing. When you have raw material like wood that you're using, the amount of wood that goes into the process, well, through cutting, through shaping, through other forms of modifying that wood, there is some loss. That is, the cutting process inherently produces wood chips and other things where some of the wood is lost or wasted, and the amount of wood in terms of volume or weight that comes out at the end is technically less than went in at the beginning. Or there's processes like a bank account where the amount of money you put in can be taken out later plus interest. So there's not waste, there's extra produced. And those are network optimizations that have yields at the nodes. So let's consider an example where a paper company specializing in recycling can take paper in one of three forms, and it recycles that into different kind of paper for different uses of three different forms. But obviously there's some waste that occurs during that process. So if you take in, say, 1 ton of paper, you might not necessarily produce 1 ton of usable output at the end. So there's a fractional amount of what can be recycled and reused in a new form. So let's look at the parameters for such a model. So 3 kinds of paper that comes in are white paper, mixed paper, and newsprint. So 3 rows here. And those 3 kinds of paper can be used to make 3 other kinds of paper products: office paper, catalog paper, and napkins, at some fractional amount. So white paper can be recycled. 85% of that white paper can be recycled as office paper. That is, I take 1 sheet of white paper, recycling it would yield 85% of a office piece of paper, okay, because of some waste inherent in the recycling process. Some kinds of input, like the newsprint, cannot be used at all to make office paper. So there's no way to take newsprint recycling paper and turn it into office paper. It can only be turned into catalog paper or napkins at a lower percentage yield. Okay. Now, because of this company having some kind of contracts where they take in this amount of paper, so businesses send this paper in, 3 kinds of paper in, to be produced, recycled. So there is some supply. That is, there is some capacity of how much of each type of paper we have, and there is some demand to be met for each type of paper we produce. That is, the recycled forms of the paper being office, catalog, and napkins. There's a demand to be met, and obviously there's some sort of profit associated with how much we can sell different types of output paper for. So office paper can be sold for $25 a ton, catalog paper for $20 a ton, and napkins for $18 a ton. But there's a limit to how much we can sell in terms of demand, and obviously we have to make those 3 kinds of paper using what we have supplied in these 3 forms. Okay. So let's move to Excel, and we will look at this kind of a problem. Okay. So we have 3 forms of paper. Say input paper type. So we have white paper, mixed, and newspaper. And we have 3 output or recycled paper types, being office paper, catalog paper, and we'll call it napkin paper. And what can be produced, we won't say cost, but the amount of output that can be produced is a fraction of how much input comes in. So 85% 90% and 95% is how much of the white paper can be recycled into the various forms of output, office, catalog, and napkin. Mixed paper at slightly less percentages of yield or output. And then finally, 0% of newsprint can be used as office paper, whereas 65% and 60% of the newsprint can be recycled into a catalog or a napkin type of paper. And then, of course, we have our supplies, represented as, 300 tons of white paper, 600 tons of mixed paper, and 400 tons. So these are in tons of newspaper. And we have demands and profit amounts. So the demand of office paper, there was 150 tons of demand for office paper, 750 tons for catalog, and 550 tons for napkin. And we can produce a profit of $25, $20, and $18 per ton of the three types. So let's format each of these numbers the way that would be intuitive. Okay. And obviously our decisions now are going to be how many pounds of each of the input types of paper do we want to use and recycle into the various forms of output. Okay. So these are numbers of tons that are going to be used to number of tons we want to use to produce that particular kind of output. Okay, and obviously each of those is going to sum up to some value that will have to be constrained to be less than or equal to the supply. So we can't use any more than 300 tons of white paper, regardless of whether we're using it to make office, catalog, napkin, or some combination of each kind of output. Okay. And obviously the columns, summed columns, multiplied, let's see here. So if we use, let's say, 100 tons of white paper to produce office stock, we would use only 85% of that would come out as actually office paper. Now, I've started laying out the problem this way. I'm going to actually pivot and say there's a different way we should want to lay this out. Because as you'll see, multiplying fractions by numbers and using the fractional numbers as our limits on demand versus the original numbers for our supply is going to become tedious. We're going to have to actually have multiple tables and different things constrained to be together. What I'm actually going to do is I'm actually going to convert this grid form into a simple row form, that is a single row for all the values. So although I've laid it out this way, I'm now going to start writing it in a different way, where I'm going to say if I want to take white paper and convert that to office paper versus white paper converted to catalog or white paper converted to napkins, okay, and mixed paper can be converted to office, mixed paper can be converted to catalog, mixed paper can be converted to napkins, and newsprint can only be converted to catalog or napkin form. Okay, so each of those values has an associated percentage yield, let's call it, and each of those values represented here in rows will also have a decision of how many tons we want to use to make that. Okay. And then we have now we have the amount of each product that we can receive. How much of that should be used to make each output type that is possible to be made from it. Okay. Now, if we simply just multiplied each yield by its how much we will use to make that particular output, then that will tell us how much output type of paper we will have for each kind. So this is the input, this is the yield, and this is the output. Okay? Now, we also want to constrain that we can't use any more than 300 tons of white paper. So whether we use white paper to make office, catalog, newsprint, or some combination thereof, we can't use any more than 300 tons. That is, we want to limit these three values to being 300. And if you'll remember, the way we did that in previous examples is we would use some product, okay, format those so we can see, some product to multiply one row by values in another row, and then we can constrain that to be either less than or equal to or greater than or equal to some other value. Okay, so here I'm going to constrain that the three kinds of use of white paper, when we choose how much to use for each process, each recycling process, that we only use 300 tons, no more than 300 tons. And similarly for mixed paper, that must be, we can use no more than 600 tons of it. And similarly for newsprint, we can use no more than 400 tons of it. Okay, so those are some of our constraints. Okay, so those are the constraints on our supply. We also need constraints on our demands. So how much office paper we produce, whether from white or mixed paper, the number of output tons we produce of that will be constrained. So this is a sum product, not of the inputs. Again, this will be a sum product of the output amounts. So we want no more output of office paper than the demand of 150 tons. And similarly for the other two kinds. So catalog paper, which can be made from three different inputs, white, mixed, or newsprint, we can produce no more than 750 tons of it. And then napkin paper, we can produce napkin paper here, can produce no more than 550 tons of it. Okay? Not sure why that is computed as one yet, but we won't worry about it. Okay, good. Oh, I know why. We needed to make these cells absolute references, and we needed to make these cells absolute references to copy those formulas down. So again, we want to multiply C13 through J13, the output amounts in tons of each output. Okay, so that's the input multiplied by the yield. The sum of those to be less than 150 for office paper. And the sum of those same C13 through J13 output tons for catalog paper only to sum up something less than 750, and so forth for napkins. Okay? And of course, the profit of each kind, so $25, $20, and $18. Of course, whether you use mixed paper or white, you still get $25 for office paper. So those are the profits for each kind of output, repeated, obviously, because there's multiple ways to get office paper. Oops. You can can either get it from white or mixed paper. There's multiple ways to get catalog paper. Okay, but if you compute the sum product of all profits by how many tons you've produced, that will be the objective. We want to maximize that amount. We want to maximize the profit we make by producing as much tons of output paper according to what profit we can sell them each for, subject to limits on our constraints of how much input we have and limits on our constraint of how much output we can sell. And then likely also we'll need to constrain that we can't use less than 0 input tons. So we'll want to make sure first that we assume non-negative, and then we can define our decision variables. We can define our 6 constraints. So each of these must be less than or equal to each of these. And then finally our objective, which we want to maximize. So let's run the solver. So this found that our maximum profit, let's format as a number, is $19,813 by using 176 tons of white paper, roughly 176 tons of white paper to produce office paper, and 123 tons of white paper to produce catalog paper. And then we're using all of our mixed paper to produce napkins and all of our newsprint to produce catalog paper, subject to we're using obviously all of our white paper supply, all of our mixed paper supply, and all of our newsprint supply. So there's no reason not to use what we have available. But obviously we can't meet every demand. Okay, so we're going to meet the demand of first office paper, for which we get a higher profit, and then we will come somewhere close to meeting the demand of napkins and not so close to the demand of meeting catalog paper, subject to what we can use left in our supply and the yields that each of those have. Make these percentages as they should have been, subject to the amount of supply we had and the efficiency, let's say, of the yield of the process for which we can make those outputs to maximize a profit. So this was a network optimization. Rather than represent it as a grid in the typical fashion, though, we converted it to another form of a simple row-based, where we can list out all of the different paths, all the different flows from inputs to outputs, one per column, and then use that standard form to set up the constraints that we want to limit each of the supplies, demands, and then obviously because we not only we decide the inputs, but those inputs are multiplied by a yield, because we don't get 1 ton of output for every ton of input. We have to multiply them by a yield to figure out how much output we have. So this is a network model, but one with a yield associated. Let's look at one more example of a network model with a yield. And some of them don't necessarily even lend themselves to a simple tabular structure. That is, there's not necessarily a set number of inputs and a set number of outputs. Like the transshipment model, there might be intermediate nodes, but it's not a symmetric relationship. So for example, let's take an oil refinery that takes crude oil, and from that crude oil, that basic stock of what it can use as input, it produces 4 outputs. However, the production of those 4 outputs go through several different processes. Okay, so for example, the crude oil that comes in can be passed through a distillation tower, which breaks down that crude oil into 2 different parts, one called distillate and one called low-end byproduct that can be sold. Okay, from the distillate, we can pass that through another process called catalytic cracking, which produces some form of catalytic gasoline and another form of high-end byproduct, which again we can sell. And then we can mix that catalytic gasoline with the raw distillate in various ways to make both regular and premium gasoline. So I'm going to step back to the whiteboard and try to represent this flow, this network optimization problem, using the standard circles and edges sort of diagram, although in this case it's not going to look very symmetric. But let's see what it would look like. So for example, we said we have crude oil coming in, and that passes through a tower process, okay? And that tower process breaks down the crude oil into two different outputs. That is, there is a distillate that comes out, and then there is a low-end byproduct, which is sellable. Okay, so that by itself is just an entity that we can sell. We can take crude oil, pass it through the distillation process in a tower, and two parts come out, one of which we just sell directly. The other part, this distillate, okay, is going to go, well, we're going to use some of it, okay, directly, but some of the rest of it we're going to pass through another process called catalytic cracking. Okay, and that catalytic cracking process produces high-end byproduct, but it also produces catalytic gasoline. Okay, and that catalytic gasoline and the distillate that we don't pass through the catalytic cracking process can be mixed in different ways. Okay. To either produce regular gasoline or premium gasoline. Okay? So, for example, for every 5 barrels of crude oil, we can produce 3 barrels of distillate and 2 barrels of low-end byproduct. Okay? And our catalytic converter process, for every 2.5 barrels of distillate that we pass in, we get 1.6 barrels of catalytic gasoline, and we get 1 barrel of high-end byproduct. So actually, there's a yield here in that you use 2.5 barrels in, and you get technically 2.6 barrels out. That is, there's some extra produced as a byproduct of that process. Okay. Now, distillate, okay, can be used, so this just passes straight through, so each barrel of distillate that we don't pass through the catalytic cracking process can be used later, mixed with the catalytic output of the catalytic cracking, okay, to produce both regular and premium gasoline. Now, to produce regular gasoline, we just need 1 barrel of distillate and 1 barrel of catalytic gasoline. But to produce premium gasoline, we technically need 3 barrels for every 1 barrel of distillate. Okay, so it's a 75-25 split. So we need 3 times as much of the high-end catalytic as we do the distillate. So just to show the process here again, we have crude oil coming in. If for every 5 barrels of crude oil we can produce 2 barrels of low-end byproduct. We can produce 3 barrels of something called distillate. Okay, so that distillate gets either used directly to make some gasolines, or we can pass, for every 2.5 barrels we want to pass through a catalytic cracking process, we can get 1.6 barrels of catalytic gasoline and 1 barrel of high-end byproduct. Okay, for every 3 barrels of catalytic we can mix with a one barrel of distillate, we can get a barrel, or we can get 4 barrels of premium gasoline. For every 1 barrel of distillate we mix with 1 barrel of catalytic, we can get 2 barrels of regular. Okay, so there's no yield there. We put 2 barrels in, we get 2 barrels out. We put 4 barrels in, we get 4 barrels out. But the mixture of how much catalytic versus distillate we use is different depending on whether we're making regular or premium gasoline. And in the end, we can sell both the high-end byproduct, the premium gasoline, the regular gasoline, and the low-end byproduct. So we're going to need to know how much each of those can be sold for. We're also going to need to know how much raw crude oil we have available as a supply. And in terms of the tower and the catalytic cracking process, there's going to be a limitation or a maximum amount of what they can produce in a given time period, say a day. So the tower may only be able to handle so many gallons of crude per day that are going to get split like this. The catalytic cracker may only be able to handle so many gallons a day, for which every 2.5 gallons yields some catalytic, some high-end byproduct. So let's look at those parameters. So those parameters look something like this. The tower capacity is 50,000 barrels of crude oil, so we'll also assume we can get 50,000 barrels of crude oil. The cracker capacity is 2,000 barrels of crude oil, okay? And then the gasoline demand, so how much gasoline we think we can sell, both regular and premium, is 16,000 barrels. Crude oil has a particular cost. Our tower has a particular cost for every barrel processed. The cracker, catalytic cracking process, has a cost for every barrel produced or processed. And then there's a profit or a revenue that we can make on each low and high-end byproduct in the regular and premium gasolines. Okay, so let me make sure I have each of those things represented here, and let's make an Excel spreadsheet for those. So again, I'm going to use not the grid form because there isn't necessarily a symmetric process being represented here. I'm going to use this sort of normalized form of a simple row where each column represents some part of the process, some part of the flow of the network. So, for example, we have the tower, and the tower can produce, or the tower has some sort of capacity, okay? Or it has some sort of amount coming in. Let's call that crude oil. So we have the amount of crude oil coming in. From that crude oil, we can produce distillate, and we can produce low-end byproduct, okay? So for every, again, 5 barrels of crude, we can produce 3 barrels of distillate and 2 barrels of low end. So that's part of our constraints that we'll have. And also from the distillate, we can use some amount of that distillate to pass through the catalytic cracking process, okay, which produces both a high end, let's represent that as how much we're going to use as catalytic input, which can be used to produce a high end and a catalytic output from the catalytic cracking process. Okay, and between the distillate and the catalytic the catalytic and distillate forms of the crude oil that we processed, we can make both a regular and a premium gasoline. But the mixtures of those two things are going to be a little different. So let's represent how much distillate we're going to use to make regular gasoline, how much distillate we're going to use to make, how many catalytic barrels we're going to use to make regular gasoline. So we'll call that cat regular and dist regular. And then how much distillate we'll use to make premium, and how much catalytic we'll use to make premium gasolines. Okay. And we're going to decide each of these things. Okay? So we're going to decide how many barrels we're going to use in all these different forms. And obviously we need some sort of objective. Okay. And we're going to have some sort of constraints. So the objective says for each low-end byproduct we make, or each barrel of low-end byproduct we make, we can sell for $36. We can sell the high-end byproduct for $44. We can sell, well, let's see, we didn't represent how much regular gasoline and premium gasoline we actually made, so we need to do that. So for each barrel of regular gasoline, we can sell for $50, and each premium barrel we can sell for $55. Okay, so those are all dollar amounts which we're going to use to define an objective function. Okay, so I'm just going to use some product like we normally use to say for each barrel of these things we can decide, only some of them, but some of them have a profit or revenue amount of each of those barrels. Okay, so that will be a currency. And now we have our constraints. Well, for each 5 barrels of crude oil, we get 3 barrels of distillate, 2 barrels of low end. Okay, so for each 5 barrels that come in, I'm going to represent that with a negative value. So 5 barrels coming in produces 3 and 2 barrels going out for each amount we produce up here. So 5 times the crude oil barrels must be equal to, so negative 5 times that, plus 3 barrels of 3 times distillate, 2 times low end must come out even. That is, those things must sum to 0. Okay, so format a few more columns to be a little bit shorter, so we can see all the values on one screen a little easier. Okay, so the sum product of all these things by all these. I'm actually going to make sure this time I make those absolute references, so when I copy that formula, it copies correctly. Okay, and we're still going to need a little more room, so let's just call this DRAG, CRAG for distillate and catalytic barrels used to make regular, and then the pre for premium gasolines. So this must be equal to 0. That is, 5 barrels of crude oil coming in must equal 3 barrels and 2 barrels of low-end product going out. So 5 in, negative 5 must equal 3 and 2 barrels of those going out. Okay. Now let's see. What are our other constraints? Well, for each distilled barrel, okay, if we have one distilled barrel, one barrel of distilled that we've produced from our tower, from the process that takes crude oil in, we can produce from that, okay, so that's what comes in. We can produce from that, well, we can use that as what goes into the catalytic converter, or we can use that as what goes into blending into regular and premium gasoline. So -1 here. So for every barrel of distillate that comes in, we can make a barrel of catalytic input to the catalytic process, a barrel of regular, a barrel of premium. So again, multiplying these things together should always equal 0. That is, so let's just say, for example, if we had 100 barrels of crude coming in, then that would produce 60 barrels of distillate, 40 barrels of low end in order to, maybe those backwards, 100 barrels coming in. Oh, backwards. No, didn't get them backwards. Oh, easy enough. For a barrel coming in, we said 3 of those barrels have to go to, make sure I get this parameter correct. Oh, I think I did get these backwards. Okay, so for each barrel of crude, for 5 barrels of crude that come in, we need to get 3 times each barrel of distillate I do have these backwards. Okay. My mistake. So again, for 5 barrels that come in, we get 3 barrels out. So for every barrel of distilled, right, we want, so 5 times that amount should be the amount of crude oil barrels we had, times -3. So to add these two together, summed up would be 0. That is, okay, again, so crude oil barrel comes in, you get basically a 3/5 of a barrel of distillate, so 60% of a barrel of distillate. So it may be easier to represent as 60%, -60%. So again, a crude oil barrel, 60% of that goes into making a barrel of distillate. Okay. And likewise, I'll have to represent this separately, a crude oil barrel coming in, 40% of it goes into making low-end byproduct. Okay? So we want to enforce that for each barrel of distillate we have at least 60% of that coming from our crude oil. Okay? So that is 60% of the crude oil gets converted into distillate. 40% of crude oil gets converted into low-end byproduct. Okay, so 100 barrels of crude would get split into 60 barrels of distillate, 40 barrels of low-end in order to meet those two constraints. Okay, now again, so let's say the distillate. So what comes in as distillate must get split between what will get fed into the catalytic converter. Okay, so what gets fed into the catalytic converter, let's start over with this one. Sorry. There we go. So again, what gets fed into the catalytic converter must come from distillate. Okay, and what goes out of the catalytic converter will produce high-end byproduct and catalytic byproduct. Okay, so let's represent that as so 1 barrel in of catalytic converter will produce, what did we say, 2.5 barrels coming in of the catalytic converter will get converted into 1.6 barrels of feedstock. Okay. So I think if you work out the fractions for that, it becomes something like say 64% of the catalytic gets converted in, or of the input, the distillate that goes into the catalytic converter, gets converted into catalytic gasoline, and 40% of what comes in gets produced as high-end output. And again, those sum to more than one because there's a yield. That is, what distillate gets used in the cracking process actually produces more barrels of high-end output and catalytic output than what went in. Okay, so copy those formulas down. We'll make sure that each of those is going to equal 0 as a constraint to the problem. Okay, now we did skip that process of every barrel of distillate gets used as either what gets put into the catalytic converter, or what we can use as distilled blend of the regular gasoline and distilled blend of the premium gasoline. Okay, so we did have that constraint. So what goes in the distilled barrels we have must be split across, not evenly, but must be split across what gets put into the catalytic converter, what gets put into regular gasoline, or what gets put into premium gasoline. So if we had 60 barrels come in, it's possible we could use, let's say, 50 of those barrels as input to the catalytic cracking process, and maybe 5 barrels each for regular and premium gasoline, and that would meet that constraint. So what gets produced as distillate gets used up in 3 different, any combination of these 3 forms. Okay, and maybe we use, let's say, 3 barrels for regular gasoline and 7 for premium. That would still meet that constraint. Okay, all right. Now we have to represent what gets output, or what the catalytic process that gets output, how that gets divided into both what gets used for regular gasoline and premium gasoline. So for each barrel of catalytic, that should get split somehow between premium gasoline and regular gasoline. Okay, so for every barrel of catalytic that gets produced out of the catalytic cracking, we can use only that many to make regular gasoline and premium gasoline as a blend. Okay, so that's another constraint. Okay, and let's see. So we're not meeting. So what gets input here is not meeting the constraint of what gets produced as high-end output or catalytic yet. So these 2 constraints, I haven't figured out a way to make those work out. But what does get used here is currently getting properly used here. Okay, and finally, we have the blend for regular gasoline. So for every barrel, every barrel of regular gasoline that gets used, we can only produce 1 barrel of for every barrel of distillate used to blend into regular gasoline, we can only produce 1 gallon of regular gasoline with it. Okay, actually I take that back. We can produce 2 because it's going to be a 50-50 split, and we have to constrain also that for every gallon of catalytic that gets used to making regular gasoline, we can produce 2 gallons of gasoline. Okay, so 1 of those gallons comes from distillate, 1 of them comes from catalytic, but they both go together to ensure that that's how, for each barrel of those we can make 2 barrels total of regular gasoline that we can sell. And then similarly for what gets used as distillate and catalytic to make premium gasoline, we know that for each gallon of distillate we will make 4 gallons of premium, but we need 3 gallons of catalytic to make that same number of 4 gallons of premium gasoline. Okay, so again, 1 gallon of distillate can be used and 3 gallons of catalytic can be used to make 4 gallons total of premium gasoline. And obviously what we're wanting to do is to maximize the objective, maximize the amount of money we can make. Okay. Now there was a few more constraints that we haven't represented yet. Okay. So these 2 constraints represent what the tower can do. This constraint represents basically the use of the distillate. This constraint represents the amount of catalytic gasoline that can be made and the amount of high-end byproduct that can be made. Okay, that's really what this is. It's the amount of low end that can be made. This constraint here, this line here, represents how we use the catalytic. And this constraint here represents how we use distillate to make regular gasoline and how we use catalytic to make regular gasoline. And this how we use distillate to make premium gasoline and catalytic to make premium gasoline. What we haven't yet constrained is that our tower can only handle something like 50,000 barrels. Okay. So whatever value here we put of barrels of crude to use in the processes, we can't use more than 50,000 barrels. So that was something like our tower capacity. Okay. And we also had a cracker capacity as well. Okay. So the cracker capacity, that is how many barrels that go into the cracking process, is limited to be no more than 20,000 barrels a day. Now there was also a regular sales or demand for regular gasoline. And I believe that was something like, there was a demand of both regular and premium. So though we can only sell 16,000 gallons of gasoline. I take that back. I think that was each. So 16,000 of regular, 16,000 of premium gasoline as the demand. So not the same. Okay. That should... one thing we did not account for was how much cost is associated. So for each barrel of crude oil, we have to pay $28. Okay. And for each barrel of gasoline that we pass through the tower, we also have to pay $5. So we're going to add to that another $5. So $28 to buy the crude oil, $5 to process it in the tower, for a total cost of $33 we have to pay for every barrel of crude oil we have, okay, or barrel of crude oil we accept and process. And then there's also a cost of operating the cracker. So what gets brought into the cracker catalytic cracking process costs $6 a barrel. Okay. So obviously the way I've set these variables up now, we're not making any money, but now we have all of our constraints specified. So we'll make these constraints constrained to be equal to their respective limits, and all of these constraints constrained to be no greater than. That is, we can use less than the capacity of the tower, less than the capacity of the cracking process, and we can produce less than the demand, but we can't produce more of any of those things than what can be handled. Okay. This is our objective to be maximized, and these are our decisions to be made. And as usual, we want to make sure that we can't make negative decisions. That is, we can't reverse any processes here. So let's solve this solution. Oh no, it is found that we should do 0 of everything. I think that looks right. Let's make sure we have every constraint represented. So the tower produces distillate, the tower produces low-end byproduct. Okay, those things, the low-end byproduct has has a sales potential. We can use some of that distillate to make either input to the catalytic cracking process or regular blending of gasoline and premium blending of gasoline. So we have those things represented. For the cracking process, for every 0.64 barrels in, we get a barrel out of catalytic. Okay, and every 0.4 barrels in, we get high end. Okay, a high end byproduct. Right. So what we produce in catalytic output can be used as both mixing for regular gasoline, premium gasoline, and then for each barrel of distillate used to mix to make regular gasoline, we can produce for every barrel used of distillate to make regular gasoline, we would produce 2 barrels of regular output. That has a profit. Every barrel of catalytic used to blend for regular, we would get 2 gallons. Okay, because both of these add up to be 2, and both of these add up to be 4s. We have limits on our tower capacity, limits on our cracker capacity, and we have limits on our demand of regular and premium gasoline. Make sure we are maximizing B6 properly. B3 through M3 are decisions. So we can decide how much crude oil to bring in. We're going to constrain basically by that how much can get split into these two things, but still we can decide how much of them get used, how much distillate gets used in various different processes. So we have N9 through N18 equal to P9 through P18, N19, N21 less than or equal to. Okay. To be honest, that doesn't, those all look correct. Don't see a mistake made. Let's just assume we did something like 10 barrels of crude, okay, which means we would get 6 barrels of distillate and 4 barrels of low-end byproduct. Okay. For the distillate, let's assume we used 2 barrels here, 2 barrels here, 2 barrels here. Okay. But if we use that many distillate in the catalytic process, we would get something like 2 barrels in would give us something like 4. So 1.6 barrels, 1.3 barrels. Somewhere close to that. There we go. And as the catalytic we got more of. Okay. And then for 1.28 barrels of catalytic, we can use that here. So let's say we use 0.6, 0.68. Okay. And obviously if we produced these two things together, we can get 2.6 barrels of that, about 2.68 barrels of that. Not meeting every constraint naturally, but we can get a positive profit. So let's make sure on this again that I did not just make a simple mistake. Everything looks correct. So, whereas this seems correct, we'll have to find the solution that matches this better. There's clearly a number wrong in the model somewhere. I'll find that and correct that and post that solution. But you can see how this network model has a yield that is so much going in is not equal to so much coming out in each case. And this network is not symmetric in that there's not a grid that can be represented easily of inputs or sources and destinations or outputs. So there's sort of an asymmetric form to what gets brought in through one node and how that gets split into other nodes, some of which are direct outputs that we can sell, some of which feed into other cells or other decisions that can be made to blend into other things, which eventually are sellable products. So we'll take another break. I'll find and fix the solution here, and then we'll move on to talking about integer and binary optimization problems as part of linear optimizations. Thank you.